So let's do the constant velocity worksheet number 5. But before I do that, I want to talk about motion maps a little bit more because I didn't get far enough in my description of motion maps the other day. You can draw motion diagrams and go from motion diagrams to position versus time graphs, to velocity versus time graphs, to verbal descriptions. We're going to do all of those in this worksheet. And so, but one of the things I wanted to go over is for a motion diagram, if you have some x-axis. Now I'm going to draw a qualitative motion diagram. Remember, this is not time anymore. In a motion diagram, this is position in meters. And this is my origin, but let's not put any numbers on here. Let's just imagine that you know, we're just going to put some dots on here. So let's say somebody does the following, okay? Let's say here's somebody walking along, and they walk along at a constant velocity, and then they stop for a while, and they stay in place, and then they go backwards. Okay, like just like that. All right. So how would you draw a motion diagram showing that? All right. Well, here's maybe the starting position, and it's good to put like, okay, this is 0. Unless otherwise stated, the time interval between dots is going to be 1 second. Doesn't have to be 1 second. You can say, like, put a dot every minute or every hour, you know, every century, you know. Actually, if you're going to draw a motion diagram for continental drift, okay, you would not want to do it every second because you have too many dots. But you might draw a motion diagram showing the plates sliding across each other and have, you know, a dot every 1,000 years, you know, or something like that. So it all depends on what you're doing. But for this class, we're dealing with little toy cars running up and down straight lines. So assume that there's a second between each dot. So you have a dot, 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 dot. Now the dots are all the same distance apart. So that means it's covering the same amount of ground each period of time. So that means the velocity is constant. So here's my velocity. Now, let's say that we're going to stop for a period of time. So this object moves here for, you know, 1, 2, 3, 4 seconds. And then we're going to stop. Now, every second, that means I'm going to be here. And then I'm going to be here again, here again, here again for a few seconds. So I'm putting dots on top of dots on top of dots as I draw my motion diagram. Is that going to work? No, because you're going to be confused about how much time were you there. So what we do is we cheat a little bit and we stack the dots. And it doesn't matter if you stack the dots above or below. Just stack the dots. I'm going to stack it below because I'm going to go backwards the other way. So I'm going to say, all right, here, 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 and here. And then I'm going to start moving backwards. But maybe I'm moving backwards at a faster speed. So here's a motion diagram, a qualitative motion diagram. Well, there is a little bit of quantitative information. If we said each dot is a second, you know time pretty well. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. Okay? So we know that in terms of numbers, but we don't know what our exact position was. All we know is that we started on the positive side of the origin, moved fairly slowly away from the origin, and then we stopped for a little while, and then we went back. Now, if I took this motion diagram and wanted to graph the position as a function of time, I can do that. Now, how much time? Well, 10 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10. And then, but this is position, but we don't know, well, we'll put it in meters. But actually, I don't even need to put the meters because I didn't put any numbers on there. So I'm not going to, just to keep it easy. And so I'm going to say, well, I'm going to start right here. So if I look on my x-axis, it's kind of starting right there. And then for 1, 2, 3, at 4 seconds, we're going to move with a constant velocity, which means I'm moving away from the origin at a constant rate. And then, so this is 1, 2, 3, 4 seconds, 5, 6, 7, 8. So all the way to 8, what am I doing between 4 seconds and 8 seconds? My position is staying the same. I'm not going anywhere. Well, but Mr. Leck, aren't you going down? No. Remember, I'm just staying right here. Why did I stack the dots like this? So I could see how many seconds I was at this location. And then I went backwards like this. So I'm not traveling down. All I'm doing is going to the right, stopping for a while, and then going back to the left. So this is going to be 0. And then what do I got? I'm going fairly fast for 8, 9, 10 seconds. I'm going down. And it looks like I'm almost to the origin, not quite. Okay? So based on this motion diagram, I would draw this position versus time graph. Now, based on this, can I draw a velocity versus time graph? Oh, yeah. Let's make it a kinematic stack. That is my time in seconds. So 2, 4, 6, 8, 10. Between 0 and 4 seconds, let's bring this down. What was my velocity like? Well, it was positive and constant. And then between 4 and 8 seconds, what was my velocity? Well, the slope of this is 0. Remember, the slope of position versus time is velocity, and from here to here, my velocity is 0. And then what do you see about my slope right here from 8 to 10 seconds? What's true about the slope of that line there? It is what? Huh? It's negative. And how does it compare to this slope right here? It's steeper, which means we're going faster. And doesn't that look at this? Doesn't that make sense? So what I'm going to do is have a negative, steeper velocity. So I'm just going to show it like that. Now, if you want to connect these, you can. Now, I was looking at some of your graphs from the previous assignment, assignment 7, and some of you are, so you look at this and you go, okay, and you're giving this a slope. Don't do that. Remember, the whole title of this unit is constant velocity. So my velocities over time intervals are going to be constant velocity from here to here. Suddenly changes, but then from here to here it's constant. Suddenly changes, but then from 8 to 10 it's constant. So all your velocity graphs are going to look like this. And then we can describe the motion in words. I can say the object started on the positive side of the origin. Okay, so you want to write, you want to write a verbal description of what's going on. Moved with a positive, constant velocity. You can abbreviate to make it go faster. Positive constant velocity for 4 seconds. Then stopped for how long? 4 seconds. Then moved with a faster velocity in the negative direction for 2 seconds. Okay? So this is kind of everything we want you to do in the worksheet. I didn't do it in the exact order that's on the worksheet, and that's okay. In this case, I started with the motion diagram. I drew the position versus time graph. From that, drew the velocity versus time graph, and then described it verbally. And that's what you're going to have to do on the worksheet here. Now I want you to do this in your notebooks. I don't want you to write on the worksheet, but and so I'll do the same thing here. I'll just do it right next to this. So the first thing you'll do, well, let's do number 1 together. I'm going to redraw the position versus time graph. Oh, this looks just like what I did. I did number 1 accidentally, except this is all qualitative. So this is position versus time. Now, velocity versus time. You just take that and say, oh, okay, and draw it as a kinematic stack. And I'll say, oh, okay, so this is what I would put in this blank. Don't put it on the blank. Do it in your notebook. Okay? And say this is number 1. And I'm going to say, oh, okay, positive velocity, 0 velocity, negative steep velocity. So this is my velocity versus time graph. And that's all I got to do. Now, a written description, I'm not going to rewrite it, but I'm not going to write it here, but I would say the object moves with a positive constant velocity, starting on the positive, with a positive position. Then it stops for a period of time, and then it moves in the opposite direction at a faster rate for a short period of time. Now, a motion diagram, you can go back, you can draw a motion diagram from this. Just this is your position axis right here. Just take your position axis in your imagination and turn it sideways. Now, there's no numbers here. I just show the origin. And I'm going to say, oh, okay, positive. Now, how many dots do you draw? I don't know. Enough? Okay? Don't draw 3 dots for the whole thing, because that's not going to describe the motion very well. But I'm just going to draw a few dots showing the constant velocity that's moving upwards like this. And then I'll stack a few dots. And then I'll maybe show a few dots going like this. And that's enough. Okay? And we're done with number 1. So what I want you to do now, and oh, we got plenty of time. I think you should be able to get this worksheet done. Now notice here on number 2. I'll tell you what. I'll work number 2 with you a little bit. Just one part of number 2. Notice that with number 2, we're given a velocity versus time graph, and we want to draw a position versus time graph. So first, let's redraw the velocity versus time graph in your notebook. And so here we have a negative velocity for a period of time. And then we have a positive velocity, but not very fast. Looks like for a shorter period of time. And then it's 0 for a period of time. So this is velocity and time. Now, I'm going to draw the position versus time graph for this. Let's extend these up here like this. Now, let me ask you this. And here's a really, really profound question. Everybody paying attention? Focus. Where do I start? I mean, look at this saying, look, I got a negative velocity. But does when it tells me, okay, at t equals 0, I've got this negative velocity, does that give me any information on where to start? My position graph? No, it doesn't. If you're going to go backwards, if you're going to go from the velocity graph to the position graph, and that's all they give you, you can start anywhere you want. Now, based on where I put my position versus time graph, where should I start? Since my slope, this is telling me, what's the slope of my first line going to be? It's going to be negative and fairly steep, isn't it? So where should I start? Well, again, you can start anywhere you want. I'm going to start up here. Why? Because that gives me room to draw it. So I'm going to go like this. I'm going to say, all right, I'm going to go like this. Now, does this match this graph? Sure, kind of a fairly large negative velocity, so, you know, negative slope. Now, what's the slope here? Describe it. What's the velocity is positive and shallow or steep? Should be a shallow slope because this velocity is fairly low. So it's going to look something like this. And then what happens? What's my velocity? 0. 0 velocity. So that means what's happening to my position? My position is not 0. It's staying the same. In other words, you're just staying, like as time goes by, your position X doesn't change. So this is what you're going to need to do. You're going to need to be able to take this graph and draw this. Now, by the way, what if somebody decided to draw it differently? Now, by the way, don't do this. This is where your written description goes. But I'm just going to draw another position time graph. What if somebody decided, well, I'm going to do this. This is position and time, and this is my velocity graph. Well, okay, I got a negative slope. I'm going to start at the origin. Negative slope. And then when you get here, you got a positive slope, but shallower. And then you get here, 0 slope. Is this graph okay? If this is your velocity versus time graph? Yes, it is. It's fine. If you want to start at the origin, you can, but remember, your positions are going to be negative. That doesn't bother me if it doesn't bother you. So actually, there are an infinite number of correct answers for if this is what's given. If this is the velocity versus time graph that's given, there's an infinite number of correct answers. I can do this. That would work. Or I could go in between them. That would work. Or I could start farther up. All of these graphs correctly describe position as a function of time if this is your velocity versus time graph. Now, why is this really profound? It'll really come up when you do calculus. Because when you go from velocity to position, you have to use a technique called integration. And in order to use integration, to get an exact integral, you have to have initial conditions. Now, if that doesn't make sense to you right now, don't worry about it. It will later on, but I'm just trying to give you some hints about what it is you're going to be doing so that when you get to calculus, it won't be quite as scary, because calculus is pretty scary when you take it the first time. Okay. All right, so there are these problems. Here I give you position as a function of time. I want the velocity, the written description, and the motion diagram. Here again, the velocity versus time graph. I want the position, written description, and motion diagram. Now on the back, written description. So copy that and then give position, velocity, and motion diagram. And look at number 6, motion diagram. And, oh, now 7 and 8 are awesome. In 7 and 8, there's 2 objects going on at the same time. And that's what we're going to be doing on the quiz on Friday. So this is really good. So see how you do on these right here. And, okay. And I'm going to give you about 30 minutes. I think you should be able to get this done in about half an hour. That is all.